This week, we are going to be talking about efficiency. And this is pretty important, especially as you go forward, as you move forward and do more difficult questions, because you're going to have to figure out algorithms that are better, right? So that's kind of what sets people apart from being just, right, like if you're to brute force it versus doing it smartly, right? Um, So we're going to be talking about how we can analyze how efficient our algorithms are, how we can describe that efficiency, how we can estimate it, and also how we can use that information to better optimize our programs. Okay, so here's the first thing. We're going to first talk about memory efficiency. So what is memory? If someone would like to just so Tarandeep, you are very close. It is RAM that we're talking about this case. ROM is read-only memory, so that doesn't really concern us in regards to competitive programming. But yeah, so memory efficiency. So you guys probably, if you guys head over, I'm gonna just start sharing my screen, even if it's just blank. If you guys head over to the judge, right, and let's say you were to go, actually no, let's go to not logged in. So, right, let's go here. If we were to just look at our problem set, for example, you can see, right, we have 1 second and 2 gigabytes of memory. Yeah, that's quite a bit of memory, right? So we're being really generous with you as to how much memory is being used. But yeah, so memory stores everything that your program kind of knows. So that's mostly we're talking about variables here, right? And individually though, variables don't take up that much space. It's mostly when you start using data structures like lists, right, where you're putting thousands or hundreds of thousands of variables into one list. That's when you really start to see your memory limit, your memory usage increase. Outside of computer programming, of course, this has a lot of applications in and of itself, right? Like for example, I'm currently running here with a measly 16 gigabytes of memory, right? So if we have a whole bunch of applications that are incredibly memory inefficient, then I'm not going to be able to run as many programs, right? But memory is pretty expensive. It's like, I think these cost me like $100. So, right, compared to a 16 gigabyte USB drive, it's quite a bit more expensive because it's incredibly fast. That's why we do need to keep in mind memory, and kind of that just helps you really. It forces you to think of ways that you can store data without having to store it twice. Or store it. You want to be able to use as little space as possible to store as much data as possible. So that's one of the challenges as well. So the main way that we can estimate our memory usage is by looking at what types of data take up how much space in Python. So if you guys, do any of you guys know C++ at all? Okay. So mostly knows. No. All right. Well, in C++, it's relatively easy to figure out the primitives. So that'd be like the ints. Right, so int will use 4 bytes of memory. Long uses 8 bytes of memory. Char uses 1 byte. However, because Python is interpreted, and you don't really have a limit, right? So in C++, when your number gets too big, it'll actually roll over. So once you get over to around 3 billion, once you go above that limit, it'll actually go into the negatives because it won't actually have enough space. Whereas in Python, you can go quite high, right? So because of this, it's very hard to predict the size of numbers in particular. And of course, on top of that, Python is interpreted. So that means that it isn't actually running directly by your computer's processor. It's actually so another program is running your program. So in most cases, we're using something called the CPython implementation, and that runs your Python code in a C program. So does that make sense? How that's kind of the difference between Python and how it's built is that's the reason why you can just take the same Python script, share it with anyone, and no matter what platform they're on, they can run it, right? Whereas with C++, right, you need to compile it for every single architecture and every single operating system. Now, of course, this makes Python a bit slower than C++. It's around 10 times slower, give or take. But people, argue like, well, yeah, it's slower, but it's a lot easier to pick up, right? And you have a lot less requirements in terms of, having to compile stuff and everything. So for some people, the trade-off is worth it. And in real life, right? In real life applications, the extra 1 or 2 seconds for most programs that you're going to be writing isn't that big of a deal. However, due to the fact that Python is interpreted, what this essentially means is, right? So let's say that in C++, right, you have a variable, and let's just say it's an 8, right? So this is all the space that it takes up. However, in Python, what happens is you have something stored as an 8, right? You have, like, let's say the number 8. Well, because Python runs on top of C, it actually needs to create another object, this time in C, and that wraps around your value that you are storing in Python, right? So it adds quite a bit more memory usage. So let's actually just kind of test the memory usage of various data types, right? So the first thing that we are going to be looking at is int. So we can use this handy tool called Sys Getsizeof. So this will allow you to get the size of a Python object. Now, it's not perfect, and especially for lists, it grossly undercounts it because it only counts the pointers in the list. But for something like a number, we can kind of see how big it is. This size is in bytes. So if we want to store a 0, let's store like 10. We can see that we're using 28 bytes. Now that's quite a bit more, right? In C++, you're using 4 for that same number. But we can see that if we try to store nothing, so a 0 basically, we can see that we're using 24. So we can kind of tell here that 24 is our overhead. So that's kind of the required amount that's being used no matter what you're storing. So the rule for integers, for ints, is that it's 24 bytes plus 10 bytes for every increment of 30 bits. So what do you guys have a guess of what that means? 4 bytes for every increment of 30 bits. All right. Well, if you guys recall, what is the basic unit in computers? Bits, right? Yeah. So zeros and ones. So whenever we're storing numbers, we're converting from base 10, which is our number system, right, to base 2, which is a bit, right, 0 or 1. So what this means is that so long as when we convert our number, we're using less than 30 placeholders in the base 2 base, we're fine. So for example, let's say 0. So when you're counting the size of an integer, you're only using everything up to the last 0 from the right. So what that means is, for example, 0001 uses 1 bit, right? But 1001 uses 4. Do you guys understand that? Yeah, so a bit is binary. That is what it is. So when we count from the left until we reach the zeros. Okay, no. So you start from the left, right? You go right until you hit a number other than 0, and then you start counting from there. So for example, 0 is 0. So that means that we're using 0 bytes, 24 plus 0 bytes, right? But let's say a number is like, no, I'm grabbing this straight out of the lesson plan. I can't do this in my head. So for example, if this was our number, if we convert this to base 2, this becomes this, right? And this, if we count it, is 18 bits. So that means that this number is going to be using 28 bytes, right? Because it's 4 bits for every it's 4 bytes for every 30 bits. So if we check that, oh, whoops, I put in the binary version of that. I had to put in the base 10 version. If we put the base 10 version in, right, we get 28, right? But let's say we have a number like this. So if we convert this number to base 2, we get this, right? And this is 31 bits, right? So 1, 2, 3, 4, blah, 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 31 of these ones. So that means that we're using two 30-bit increments. So that means that we have 8 bytes of storage for the number, plus the 24 overhead will give us 32 bytes used. Okay. Does that make sense? Is everyone following here on how we're determining the size of these numbers? All right. So that's it. That's int. Right? You can say, well, right, they take up, right, more than like 7 times the 7 times the size. It gives you the flexibility that you don't need to use different types for different types of numbers, right? So that's the trade-off there. So you just have to be cognizant of that. Now with a float, it is just 24 bytes. All right. And a Boolean is 8 bytes. So true or false is 8 bytes. Now, if you do sys.getsizeof, you're going to get 28 bytes. Now, this isn't actually how much is getting used. So recall this, right? So what's happening whenever we wrap it is what's in the C program that's running your Python, essentially an object is getting created. So it's called a CPython object, right? So this CPython object is what's actually holding all of your data. In the cases of true and false, this CPython object is 28 bytes. However, because there's only true and false, right? There's only true and false. You don't need to there aren't any other types of Booleans. Essentially what happens is in a program, you only have 2 instances of true and false. And every other instance of true and false is actually something called a pointer. So that's essentially just a copy that points to the actual object. So we call this a singleton. So I'm just going to stop there and let you think about that for a sec. All right, so every single Python value is getting stored as a CPython object, right? So this is what we're measuring the size of. However, with this case of true and false, we're only creating one of those objects. And instead of creating a new object every single time we use true and false, we are just pointing to the object, the true and false object that we already created. So that saves us quite a bit of space. So does everyone get that? Because that is a bit hard to wrap your head around. Okay, all right. How about this? Let's go into what a pointer is. Does everyone know what a pointer is? Does anyone know what a pointer is? Okay, so none of you guys know what a pointer is. Okay, so that's fine because you wouldn't have run into them before yet, or you might have, but you kind of just brushed it past. So whenever we have a variable, let's say we make a variable called v, and we're going to assign it a value of 8. A value of 8. So what we're storing inside this is the value, right? So imagine that every single variable is a box, all right? And the value of the variable is what's inside the box. So in the cases of objects, what you have is instead of storing the whole object. So for example, if we were to store like an object that you know of, for example, the whole list, right? Instead of storing this whole list inside the box that is the variable, what we do is we actually store it separately. Instead of storing this whole list here, we're going to store a location. We're going to say So for example, RAM is organized kind of like a table. So we have, right? So we have an address. So, and whenever you ask for an address, it'll give you the value that's at the address. So for example, if we were to have 0, 1, 2, 3, and like A, B, C, right? In the case of a primitive, right? So that's your ints, your booleans, etc. What's being stored at the variable's memory location is literally just 8, right? However, if we were storing something like a list or an object, instead of storing this whole list over here, which you can see, it'll be very interesting to fit into this whole section, right? What we do is we store a pointer. So we say, okay, well, the whole list here is going to be at B3. So now, if we just want to access the object, instead of having to create a whole new one, we can just say, oh, hey, go to B3. We go to B3, and then we can store the whole list here. And just there are many reasons why we do this, but just for now, just accept the fact that we just store it separately for reasons. We store the list over here. So that's essentially what's happening in Python. So instead of having multiple Boolean objects, they literally just have one object called true and another one called false, right? And because that has a lot of overhead, right? It has that 24-byte overhead because Booleans are implemented as numbers in Python. So it has a pretty big overhead. So we want to minimize that. So how do we minimize that? Well, true is true and false is false, right? You can't really say there aren't properties of true, if you get what I mean, right? It's either true or it's false. There's nothing in between. There's nothing additional, right? So what we do is whenever we create a variable that has the value of true, instead of creating another true object, we just say, hey, this is equivalent to what's the thing that's over here in B3. Yeah, okay. So the true cost, so in C, the pointer size, so this is called a pointer. So whenever we are referring to another address in memory, it's called a pointer. So the size of that pointer in C is 8 bytes. So whenever you're creating a variable with the value true or false, it takes 8 bytes. Okay, so it doesn't take the 28 that's here. It actually takes 8 because it's actually pointing to that object. It's not creating a new one. All right. And finally, we have strings. Now, strings, I'm not going to go into too detailed why these numbers happen, but we can just say that strings are 49 bytes plus 1 byte for every single character. If we have an empty string, it's 49. If we have just A, it's going to be 50. And AB is going to be 51. What about comments? Well, comments aren't part of your Python program. Remember that? It gets ignored. So comments don't really, other than the space it takes up on your hard drive, it doesn't take any memory. Right? So we're talking, whenever we're talking about memory usage, we're talking about what your program is running. But if you guys remember, comments are not run. Okay, so let's everyone get, so just to recap, numbers take 24 bytes plus 4 bytes for every increment of 30 bits. Floats take 24 bytes. Booleans take 8 bytes. And strings take 49 bytes plus 1 byte for every character. All right, everything else is variable, right? Lists will depend on how big, how many things you have in it, right? Different objects will take different amounts for whatever they need. So we're just talking about primitives here and the most common ones that you're going to be using. Okay, so if you guys think about this though, right? 51 bytes, right? There are so many bytes in a gigabyte or even in a megabyte, right? Really need to worry about it too much. So for example, a megabyte. Does anyone know how many bytes are in a megabyte? Yeah, a million. So these use the metric prefixes. So mega in metrics is 10 to the power of 6, right? So that's a million. So if you think of that, that's like, well, you can put, right? If we're just storing numbers, we can say, and that's 1,000,000, divide that by 28. We can store 35,000 variables, right? So if we're doing that by hand, obviously that's not going to happen, right? The main place that we really need to think about this is when we are adding large amounts of data to lists and other data structures like sets or whatever. So now here's another thing that really kind of sucks about Python is that whenever you're creating a list, you have the overhead of the list, right? So you have 56 bytes for the overhead. However, in addition to having to create essentially a hidden separate variable to actually store the data, the list itself doesn't store any of the data. All it does is it stores pointers to the data. So that means that whenever you're storing something in a list, not only are you using the base amount, so whether that be 24 plus 4 for ints or 49 plus 1 for strings, you also need to pay additional memory for the pointer that actually points to that quote unquote hidden variable. So that means that lists love to gobble up your memory, right? So that's really where we need to pay attention. And that's true for a lot of the data sets, is that it isn't storing the data in the container directly. It's actually storing a reference to another object that it creates to store your value. So for example, your list doesn't actually contain 888 or whatever. It contains A0, right? No, for example, like 8. This might be confusing for some people. So we're going to say like 8, 9, 10, right? It's not storing 8, 9, 10. It's actually storing A0, A1, A2, right? And then on top of that, this thing is also an object in and of itself. So you're paying a huge amount of memory for these things, but you have to, right? So does everyone kind of understand memory usage? How we can estimate it, right? So we don't need to get an exact number for every single program. We just need to estimate to make sure that we are around how much the limit is. So next up, we're going to be talking about something that's going to be a little more important, especially this year in junior. Memory, you're going to have to think a lot about memory efficiency later on. But what is kind of really important and something that we've already hit against is time efficiency, right? So we call that time complexity, is how we describe how time efficient our algorithm or our program is. Right? You guys probably remember last week, right, when we were trying to solve that J2, the epidemiology question, right? How we got time limit exceeded. So this is kind of how we are going to learn how to analyze our programs, and we're going to learn how to describe the efficiency of our algorithm, and then we can also learn ways to make things a little more efficient. Whenever we're describing time complexity, we use something called big O notation. Has anyone heard of big O notation? So what big O notation tells us is the relationship between the number of inputs and the number of operations that our program needs to do. Let's take this. Remember, guys, this is the relationship. It is not an absolute number. It is a relationship that you can plot on a graph. Okay, so you generally see like, right, this would be input, and then you'd put like the operations, right? And you can have like that or whatever. So let's take a look at a sample piece of code. We're going to keep it simple for this week because we're getting started. Take a look at the sample of code. So would the number of, so our variable here would be n. So that's going to be our input number. So can you describe the relationship? So whether is it linear, is it quadratic, is it absolute value, is it constant or whatever? Can you guys kind of, I'll give you guys around like 5 minutes. Can you guys kind of maybe guess to see what it is? All right, so we're looking for the amount. So as n grows larger, how does our number of operations grow? All right, most of you guys are saying you don't know, which is totally fine. Let's look at every single line and let's see how much time they'll take in relation to their inputs. So line 1, we're initializing a variable. This is constant time. So that means that no matter how big your input is, it takes the same amount of time to initialize a variable. Okay, so we denote constant time operations as O at 1. So O at 1 is constant time. Can I just erase this? So constant we denote as, oh, that's a bruh, at O at 1. Okay, so let's look at this loop now. So it is essentially saying that we're going to run this loop for the amount of times that n is, right? So as long as n is less than, x is less than n, we're going to increment x. This is our indication. So this part of the code runs in linear time, right? So if I put in 1, I'll get out 1. If I put in, I'll do 1 operation. If I put in 5, I'll do 5 operations. And the key is, guys, it's not the number that matters, okay? If I add 2, this would still be linear. The key point is essentially if you were to draw this relationship, this is how I've kind of, this is my strategy, is to visualize the graph, okay? So if I were to do, if we're to plot this, right? Okay, 1 operation is 1. Input of 2, you get 2 operations. 3, you get 3 operations, right? So this is a line. So that tells us it's linear, okay? But 2 is the same thing, right? If we add by 2, all we're doing is we're increasing the slope of the line, but it's still a line, right? No, I can't draw this very well. No, that looks like, okay, you guys know what I mean, right? It's a steeper slope, but it's still a line, okay? So please don't fall into that trap. Look at the relationship. Don't look at the numbers. Well, look at the numbers, but like look at the relationship between them and not them just by themselves, okay? So given this, we can probably say our program is O at 1 plus our print statement. So that's another O at 1. And the whole loop is O at n. Right, so we can probably say it's O at 1 plus O at 1 plus O at n. Okay. However, we're using big O notation as a way to approximate the time complexity. So that means that, so think about it this way, okay? Let's say I put in n equals 10 million. Are those O at 1s going to really matter? Right? The answer is no, right? Right. As you increase n larger and larger and larger, the smaller the time complexities with a smaller exponent matter less and less, right? So that means that we're just going to say it is O at n. Let's take a look at this one. So what do you guys think this time complexity is? I'll give you guys a few minutes to look at this. Most of you guys aren't quite sure. That's okay. Again, this is our second question. So let's look at this. So actually, let's compare it with the one that we just had. So the first one that we did was this one, right? So we know that this example is linear. And if we look, right, it's essentially the same thing. So we know that this outer loop here runs in linear time. However, we also have another loop inside this. And this loop, right, it's essentially the same, right? It runs, if you just look at this loop by itself, I think we can all agree that it is linear, right? So as n goes up, the amount of operations it does increases linearly. So what we're doing here is we are running an O at n loop, O at n times. Does that make sense? So we are running an O at n loop, this loop, O at n times. Then we can literally just multiply it and we can say that this whole loop runs O at n squared. So it'd be quadratic. O at n squared, right? O at n times O at n equals O at n squared. Third one. This one's going to be a little more tricky. Oh, if n is greater than 0, how can n ever become 0? Oh, let's just say 1 then. Although we can see, just due to the imprecision of floating point numbers, it'll probably terminate. Yeah, it terminates. Yeah. So even if it is 0, due to the fact that we're going to have a lot of imprecision. At a certain point, it's going to be such a small decimal that unless you're using huge amounts of memory, it's going to be basically 0. So this will evaluate to 0 due to the fact it's going to be a float, and there are a lot of intricacies with that. But just for your logic's sake, yeah, we can put it as 1. So most of you guys still don't know, which is fine. Let's take a look at this. So what we're doing is our loop, what it's doing is it is essentially having n over and over and over again until it reaches 1. Okay, so think about this in a math kind of way. When you're having it, what does this depend on? Right? The amount of times that it's going to run is going to be dependent on the number of 2's that are in that number. Right? So given that information, we can conclude basically that this is log base 2 n, right? However, there aren't really that too many algorithms that run in log base 10 of n. So in our case with big O notation, log n actually means log base 2 of n. All right, so this is log n time, right? Because we're seeing how many 2's are essentially in the n, and that's what a log is. So this is like the number of powers of 2, just because that might have been confused with division. All right, we're looking at how many powers of 2 are inside n, approximately. Does everyone get this one? This one confuses a lot of people. Next up, we're going to look at this. So assume that list is a list of n numbers. Okay, so it looks like most people are sure now, which is good. All right, so either between linear and quadratic. All right, so let's look at this. So this one, we can agree, is linear, right? So as the size of the list increases, the number of operations will be linear. This one, we can probably say it's quadratic, right? So the inner one is n, and then the outer one is n, so that's n squared. So then what do we do here, right? So essentially, do we pick between n or n squared? So let's go back to the first one we did. So remember, right, initializing a variable O at 1, right? And we added them up, so it ended up being O at 1 plus O at 1 plus O at n, right? But remember, again, that big O notation is we're using this to approximate the amount of operations versus the input, right? So let's say that a number, so right, if we were to say 1 input, right, then yeah, it's a pretty big deal because it's literally half of the operations. But let's say we increase that number to 100,000, right? N squared is going to be so much larger than O at n that at that point it's going to be irrelevant. So in this case, we're saying that this program runs O n squared. All right. So always take the highest power, or yeah, in this case, we're taking the highest power. All right, basically, we're looking for the most inefficient one. And that's going to be the one, because as we increase our values, that part of the program is going to be what hogs most of the operations. Okay, so as a reminder, make sure you're looking at the most inefficient part. And that's what we're going to be naming our algorithm. Right? It's kind of like when people say, right, like a small group of people ruin it for everyone else. This is kind of the idea, right? It's if one part's super inefficient, we're labeling the whole algorithm as that inefficiency. Now, do note, guys, that especially outside of competitive programming, not every operation takes the same amount of time, right? But again, just please keep in mind that we're using this as a tool to approximate the number of operations, all right? So now that we know how many operations are happening, how can we tie that into figuring out if we're going to go over the time limit? Well, we're going to have to know how many operations Python can do in a second, right? Now, again, this one also fluctuates quite a bit, right? Depending on a variety of factors. However, in general, we can say that Python can do around 10 to the 6 or 1 million operations per second. So to test whether an algorithm is going to fail the time limit, we can say, okay, what is the largest input they're giving us? Then we're going to put that, we can put that into our time complexity, right? So like, for example, if n is 100 and our algorithm runs n squared, well, we can say that it's going to take around 10,000 operations, right? So if we say it takes around 10,000, then we can divide that by 1,000,000, and we can see that that is quite a bit less. It'll take around 1/100th of a second, right? So if our time limit is 1 second, we know that we're good, right? But for example, for that J2 question for epidemiology, when we had 10 million, but then after we had, okay, sorry, a clarification. When I'm saying choose the biggest number, I'm saying choose the number that would cause the largest amount of operations. So for example, in J2, when we decrease the power is actually when we cause more operations to happen, right? So that's going to be when we should be testing. So, right, it was like 10 million was the upper bound, and we're starting at 1 and we're increasing by 1. Well, that meant that was going to take 10 million operations. Python can only do around 1,000,000. So that means that it's going to take 10 seconds, but we only have a time limit of 1 second. So that tells us that we need to do something to improve that. Now, for example, here, I just like to point out here that if you're doing this, please don't do this unless the problem somehow forces you to. Like if you need to print every single number in the list before you print this, right? Generally, like it's better if you just loop through it once. But of course, if it forces you to print all the numbers first, then there's not much you can do. Just keep that in mind, though, right? Because even though some things may take less, are more efficient, that doesn't mean that you shouldn't try to keep it as efficient as possible. Okay. So what I'm going to leave you guys with is, well, we're going to come back later to take these up, but I'm going to send a list. So I have here 1, 2, 3, 4, 5, 6, 7, 8 little algorithms here. Okay, so what I want you guys to do is to determine the time complexity of each algorithm. So head over to Junior Resources and please take a look at these. And then we're going to come back in 30 minutes. So okay, at this rate, it's going to be 5:20. So we're going to come back at 5:20 and we're going to take these all up, okay? But let's just go down the list. So number 1, what do you guys think?
It should be constant, right? Because
yes, it is constant, because no matter what you put in, you're always running it 20 times. Wonderful. How about B?
log time.
Yep, log, right? We're dividing by 2. All right, these numbers don't really matter too much. Especially this one doesn't really matter at all. We're just decreasing it by half. How about the third one? This one.
I think quadratic.
Yep, it's quadratic. Because if we look, whatever we're doing in here isn't really doing much anyway. We can basically ignore it, and we can see it's just 2 loops. This is an O at N loop, and this is O N loop 2. So that's quadratic. Okay, question 4. So it looks quadratic, right? Because you have these 2 loops. However, look at, right, whenever j is greater than 5, we break. So if we start increasing these values more and more, what's going to always basically end up happening is that this loop right here basically runs the equivalent of constant time, right? So then what we have here is just O at N. Does that make sense to everyone? So look, if we see here, j is greater than 5, we break, right? Most of the time, as we get bigger and bigger, this is going to be greater than 5. So we're going to be breaking automatically at 5 every single time. It's going to take the same amount of time, no matter if the length is 100,000 or, 10. It's still going to do the same amount of operations. So this part is constant, and it's being wrapped by something that is linear. So thus, it is n times 1 is just n. Okay, next one. Question 5. If we look at this, we see that we are increasing n by some n. We're increasing x by some n, right? But look, this looks n mod 5. So this looks a bit kind of weird. However, we're seeing that we're not actually updating n at any time. So that means that this is equivalent to us just adding some number to x. So then if we're doing that, this is essentially just a basic for loop. And that runs linear. All right, so this is O at n. Next one here, question 6. Does anyone have any takers? So this is c is less than n, okay? So c is 1. Then it's okay, a plus 5, then b times equals 2. So we're multiplying b by 2. And then we're going to take the max minus the min. So let's think about this, okay? Because remember, if a good strategy when determining these things is to look for really big numbers, to try really big numbers. Because if you try small numbers like 1 or 2, it's going to be you're not going to get the best result. However, when you have bigger numbers, you're more easily going to be able to see what's going to happen more often, right? Because when you're starting these small numbers, right, every little thing matters. But as you get bigger, the smaller things start not mattering anymore. So let's think about this. We are increasing a by 5 and we are multiplying b by 2. Well, after we run this for a while, we'll see that b is always going to be greater than 2, always greater than a. So essentially what we're doing is we're going to be saying c equals b minus a. However, as we increase the amount of operations, we'll see that b is going to get so big that no matter how much we subtract, it's going to be basically around the same, right? So let's say b is like 10,000, a is like, let's say 100, right? 9,900 is still pretty close to 10,000. It's effectively 10,000, right? So what we can do here is we can just generalize and say most of the time b is multiplying by 2, right? And because we're saying c, so this will basically be saying c, so now this turns basically into c equals b, right? And because we're asking when c is less than n, we're cutting the amount, we're basically, we're reverse cutting, right? So we're starting small, and then as we grow larger and larger, we're going to be, we're approaching n quicker and quicker. So, and that's by power of 2. So that means that this is going to be log n, right? Because we're going to be doing log n operations because we are multiplying by 2. So this is a really good example of how we really need to make sure that we are looking at the big picture. Because this will really trip you up if you're just thinking small numbers. If you start thinking large numbers, you'll quickly be able to see that what we're doing is we're essentially multiplying b by 2 every single iteration. And that's going to be log n. Next up, question 7. This is linear. And the reason for this is you might say, okay, well, we're multiplying j by 2, right? But look at the condition. It's saying if I is even, right? But I starts off as 1 and it's increasing by an even number. So that means that I is always going to be odd. That means that essentially we're going to ignore this. And now all we're doing is we're just increasing j. So then we can obviously see now that it's linear. Okay, and then this last question is over here. So essentially what we're doing here is we are generating a random number. And then if that random number equals j, we're going to break. So what do you guys think? What time complexity would this be?
Factorial?
It would not be factorial. Do you have a reason why you think it's factorial?
Never mind.
Okay, so do you have an idea of what you think it could be?
Quadratic.
Quadratic? Yes, it's quadratic. And the reason for this is, right, although we have a condition where it's going to break, as n increases, right? If we go to 10,000, the probability that this is going to happen is so small that most of the time we're effectively going to be going through the whole loop. And as our values increase, the longer it's going to go, right? So this is essentially going linearly. And then we have another loop that's going linearly. So it's going to be quadratic again. So remember, this is again an example of when you really need to take larger numbers and try them, right? If it's a smaller number, right, it's going to be a little different, right? It's going to be, it might be a little more, it might break more often. But as we increase over and over again, and as we increase the amount of operations we do, as we increase our input n, you can see that this break is going to happen less and less often. So it's going to be on average basically O(n) squared. Okay, so that's our lesson on time limit on efficiencies. I know this is a bit more of a boring one, a bit more of a lecturing one, but this is really an important concept, and you're going to really shoot yourself in the foot if you don't understand this for contests. Because that TLE is one of the most infuriating things, because you can literally have everything right, but if it's too slow, you're not getting points, and you're most likely going to be getting time penalties as well. All right. So I'll be posting some more questions, just determining the complexities, probably over the weekend. I still need to find some of them. And I'm also taking some from Mr. McKenzie, but his is in Java. So the ones that I'm using for him, I need to actually translate to Python as well. So I'll probably get those up by Saturday, most likely around Friday. But other than that, thank you guys for coming out, and I hope to see you guys next week.